Hi, I'm Dr. Nijisha Chajar, Assistant Professor from Department of Biomedical Engineering, SRM Institute of Science and Technology, Katanglupur. So for this subject, Principles of Medical Imaging, I'll be taking Unit 1, X-ray Imaging and Digital Radiography. So in this video, we will be discussing nature of X-rays, properties of X-rays and production of X-rays. Let us start the session. So before we go into understanding X-rays, let us see what do you mean by radiology. Radiology is nothing but the study of radiation. It is based on the fact that various anatomical structures, you have the various structures in the body, the heart, the different organs, the different veins, arteries, muscles, everything. Each and every part has different densities. Now, what happens is because of this density, imagine I'm sending some radiation, some X-ray radiation into our body. In that case, what happens is based on that density, different part of the organ, different sections of the organ will absorb in different intensities. One might absorb more, one might absorb less. So what happens, I'm sending X-ray from one side, in behind, based on what are the organs that are present, I might get different intensities of radiation which are coming outside of it. Now, why do we use all this is based on this, this will help you in understanding the spatial intensity variation, spatially, location-wise, how it is being varied. So hence what we are doing is the same X-rays are used in medical diagnosis. Diagnosis meaning that I want to find out if there is any issue or not. Why do I use X-rays? They have first important properties that they can penetrate. Penetrate meaning that they can go deep inside, and based on what material it is, they can be absorbed, and different materials will absorb differently the X-rays. Second thing is, once you get the X-rays which are coming out, that can be seen visually. How? By using luminescence principle. That is, I can use it to produce a colored output, and hence I can see it as an output. With this is just the basic setup of a diagnostic radiological image formation process. So you have an X-ray source here. You're focusing it into a structure. So this assume it as the body. So in this you have the bone, you have the tumor, you have the tissue, you have air. So there are different, different structures present inside, and each of these structures have different density. Now what happens when I send an X-ray is based on what structure it is, the absorption will vary. So tissue, you can see here I have the whatever is the radiation that is coming out is of different intensity. When there is bone, the bone will absorb the X-rays, so hence the amount of X-rays coming out will be less. Now again here it is more. Here there is a tumor. Again tumor will absorb not as much as the bone, but it doesn't allow totally, it will absorb. So you can see a small difference in the amount of X-rays which are coming out. Now you have air. Air also will allow directly the X-rays to go. So you can see here X-rays are coming out, again the tissue. So this profile, this profile is called as a spatial distribution of intensity. So based on this, we are using it for diagnostic radiology. So let us study before we understand how it is used, we need to know the basics. So nature of X-rays, they are called as electromagnetic radiations. So they come in that spectrum, and specifically they have low wavelength in this spectrum. So if you see here, you have the lower wavelengths are, these are the lower frequency signals, these are the higher frequency signals. Wavelength wise, these will be the lower wavelength signals. So it is just opposite. Both of them will be in opposite. So if you see here, you have the high frequency signal. This is the second high frequency. In that case, we have the low wavelength signal. X-rays comes just after the, just before the X-rays, gamma rays. They have wavelength of order of 10 to the power of minus 10 meter. They propagate with the speed of sound, that is 3 into 10 to the power of centimeter per second, and they are unaffected by electric and magnetic field. So if you have any magnetic spectrum, nothing is going to influence it, whereas there are some ways which will get affected by your electrical and magnetic waves. The nature of the X-rays, Once again, whatever X-rays that are produced, it is directly dependent on the voltage with which the radiation is produced. So if I use a high voltage source, then naturally I'm going to get a high energy X-ray. So that is the concept. So characterize the X-rays by the voltage. So if you see E is equal to h nu, we have the formula. Nu can be substituted by the speed of light formula. So C by lambda. So this is the basic concept of energy. So energy, that same concept we are applying here. The properties of X-ray. So before we are going to apply X-rays to our body, we need to know what are the properties of that. So first important property is they can penetrate through material, which means that they can allow it to pass through, and they can also absorb and reflect visible light. So that is another important thing. Second main property is they are absorbed and passing through matter. So first thing, they will allow to go. When they go, they get absorbed because they have short wavelength and they have extremely high energy. The extent of absorption, how does it depend on? It depends on the density of the matter. Very important property. Then X-rays, they produce secondary radiation. What do you mean by secondary radiation? It means that this X-rays, the energy can be converted to produce some other radiation. So usually they are scattered radiation, characteristic radiation, and electrons. We'll be seeing the different types. Then X-rays, they produce ionization in gas. So imagine I'm putting X-rays, I'm illuminating it within a gas. In that case, they can create ionization, split the ions. They can influence electrical properties of liquid as well as solids. So because they are ionizing, they can create charges. Okay. Then X-rays also produce fluorescence, very important property for diagnosis, which means that they can emit light. So you have a dark, you put X-ray, they can glow. Okay, so this is another very important property. These are the important properties of X-ray. So let us see what are the units of X-ray radiation. Given the International Commission, they have finalized, or they have given Roentgen as a measure of the quantity of X-ray. So Roentgen is the person who invented, who found out X-ray. So based on that, they have given the unit of radiation. So X-rays, the unit is Roentgen, and it is based on the ability of the radiation to produce ionization, and this is how you define Roentgen, and you write it as R. So 1 R, like that you write it. So 1 R is the amount of X-ray radiation which will produce 2 into 10 to the power of 9 ion pairs. So based on how many ions you produce, that X-ray quantity, that amount is written as 1 R. So this is the standard definition of 1 R. So you have milli-Roentgen or micro-Roentgen. Based on that, you can be used. Now the unit of absorbed dose. Now when it comes to dosage absorption, this Roentgen is the quantity of X-ray, but dose absorbed means you call it as rad. Very important unit. So how do you define rad? It is a radiation dose which will result in an energy absorption of 1 into 10 to the power of minus 2 joules per kg in an irradiated material. So you have an irradiated material, how much energy is getting absorbed? That energy absorption is nothing but the radiation dose. Okay. It is approximately equal to the dose absorbed by soft tissue when it is exposed to 1 Roentgen of X-ray. So 1 rad is nothing but equivalent to 1 Roentgen X-ray absorption. That is a very simple way to remember it. The production of X-rays. Now, how do you produce X-rays? How are X-rays produced? Very simple. When an electron, you have an electron, it is going to be very, very fast running electron. When it goes and collides with the matter, at that time what happens? The energy is not having any other place to go, right? So that time it gets converted in the form of light. That's all. That light is nothing but X-rays. So the energy which is possessed by the electron, which appears from the site of the collision as a parcel of energy in the form of high penetrating electromagnetic waves. That's all. That only you are going to take it as X-ray. So you have a GIF here which you can see. So you have a place where electrons are produced. You are increasing the speed of the electron by creating a potential, and once it goes, there is no place for it to go, so it goes and bombards this metal target. When it goes and bombards it, when it collides it, it doesn't have any other place to go. That energy has to get converted. It gets converted in the form of X-rays. Very, very simple concept. Okay. So X-rays are produced in specially constructed glass tubes. So we cannot do it in anything like that because you have electrons, all these concepts. So you have it in a glass tube. So what are the main important components for production of X-rays? First, you need to have a source for the production of electrons. So I need electrons. So first I need the source for the electrons. So that is nothing but the cathode you call. So cathode, they are negatively charged. Why do I need negatively charged? These are going to give me electrons, and these electrons have to go far away. So this is negatively charged. The second important thing is an energy source to accelerate the electrons. Now this cathode is having so many electrons. This electrons now has to get accelerated. It has to move fast. For that, you're going to create a positive part, that is the anode. Okay, the second thing is the third component is a free electron path. So there must be a space for the electrons to get accelerated. So this path. Then a means of focusing the electron beam. Then I need to focus it. So it must not go that way. It must all get focused into a specific target. So that is important component, and a device to stop the electron. That is nothing but the target. This is nothing but the anode. So you have the very important components, one electron generator, an electron accelerator, a path, then you need to have a target, and then a overall containing source. Okay, the whole important part. So this is nothing but the main important component. So in this you can say very importantly, when you're doing this type of procedure, when you're using this X-rays and all, you have two types of spectrums which are produced. So first we will see what you mean by this Bremsstrahlung spectrum. So this is nothing but whatever concept that we told now, no? In that way, when the X-rays are produced, they are called as a Bremsstrahlung spectrum. So we'll see one by one in detail. So what happens here? You have an anode. First thing is an anode. So you have a you have a cathode which is a negatively charged. So here you have the electrons which are generated. So the cathode electrons are getting generated, and then you can see it is negatively a high voltage source. Why do I need a high voltage source? Because I need more number of electrons, and the electrons have to get accelerated. So I have a high voltage source. I'm going to give it to the negative to the cathode. Here the electrons get generated. I need to now speed up the electrons, so I'm going to connect it to an anode which is positively charged, and it is connected. Now in between here I need to focus it, and I need to focus it and fall it on a target. So this is your tungsten target. So this target, when the electron goes and falls, X-rays are generated, or the whole component is being enclosed in an envelope, so that but the main reason is the X-rays, if it gets interacted with a gas or any other particle, you lose its the energy. So that is why it's all done in an evacuated envelope or tube. Now to understand how one electron is going, it is going and hitting a target, and suddenly I'm getting X-rays. How does it do? For this I need to know this Bremsstrahlung spectrum. So how does it happen is, now imagine you have an electron here. This is your matter, that is a tungsten, okay, the target atom. So each atom you'll have a nucleus which has the protons and the neutrons, then surrounded by the different types of electrons. Okay, so you have the electrons surrounding which are revolving, you have the proton and the neutron. Now you have first condition, let us see this one. Okay, this is an electron. This electron is coming very fast. If it goes and hits then directly, if it goes and hits your nucleus, okay, now what happens is there are two possibilities it can go. Okay, so one way is it can directly hit the nucleus. One way is it can just go glide around the nucleus. The third way is it can go not away from the nucleus. So there are three possibilities. One by one we are going to just see. So if in case it goes close and directly into the nucleus, when it goes, at that time what happens is you have it to be maximum impact happening in that point. In that case you have a high energy X-rays produced. Okay, so this totally, because it's coming and totally it is getting stopped, this releases, this whole kinetic energy is getting converted totally into an X-ray. So this, based on this X-ray impact will be high, and the high energy X-rays are produced. What happens when doesn't go directly close, but just goes a little bit close to the nucleus? In that case also what happens is you can have an interaction that be a slow, but only this whatever deceleration, the speed reduces, the deceleration, because of that you have X-rays produced, but the X-ray energy will be little bit less when compared to the direct interaction. And you can see that it's the energy of the electron becomes lesser. The third condition is it can just not go and interact with the nucleus. It can go somewhere away from the nucleus. Okay, you can see here the third electron. In that case, what happens is that you'll have again an X-ray produced, because as a deceleration, it is reducing in intense, the speed is getting reduced, kinetic energy is reduced. So you have an X-ray produced, but what happens is it will be a low energy X-rays. So that is the reason why when you have an X-ray, no, when you're producing X-rays using this metal target, all that, you have the energy of the spectrum something like to be like this. So you have all energy spectrum. You'll have maximum, you'll have minimum, you'll have like this. So you'll have an average, you'll have minimum, you'll have a maximum. All the type of spectrum will be available. So this is how this concept, no, of an electron going and interacting with a target atom to produce X-rays is called as a Bremsstrahlung spectrum. Okay, so this very important is how they are produced. Only if you have this energy, no, is of 20 to 150 kilovolt. Very, very important. So to produce this type of variation to accelerate the electrons, I need 20 to 150 kilovolts. So the X-ray machines are such high voltage equipments. Cathode, very important, the negative electrode, and this will produce the electrons. Anode, the positive electrode, and this will be the place where the target is produced. So everything whatever I explained is there available in this slide. So you have the electrons, they are going to fall on that, so they can decelerate and change its direction, which will be produced in the form of Bremsstrahlung radiation. So Bremsstrahlung is nothing but these electrons, they are going to go and interact with an material, with an atom, with the matter. In that case, what happens is the electrons, they decelerate, the loss of kinetic energy is getting converted in the form of X-ray photon. Now the amount of energy lost is only nothing but the energy of the resulting X-ray. So this is how very simple to understand the Bremsstrahlung radiation. You can see here. So if you see, you'll have in all the way, can you see here, it can be from 0 to 90, all types of radiations will be available. So what do they usually do is, they will filter it. They will try to remove unwanted radiation to get this red color line. So filtration is nothing but you are going to remove the X-rays by attenuating in materials that inherent the X-ray tube. So you have a window. In the window, what happens is, window is nothing but you can assume, no, something like a window, the exact window where it's a thin aluminum or a copper sheet. What do we do? That is this very, very low energy X-rays, no, you remove it and you try to bring it to a particular spectrum, so that I know that in which energy my X-rays will be. So this is called as a Bremsstrahlung, because I'll have low, high, everything I'll have. Now I'm going to bring it to a particular energy, kilo electron volt energy X-rays. With this, we will complete the Bremsstrahlung spectrum. Thank you.